Hello, this is Dr. Ryan Johnson with the course Introduction to Statistics. Here we are doing section 9.3 in the reading, but it's 9.4 in the worksheet because there's an extra section on chi-squared that we're skipping. So you should have already read section 9.3, and one of the things they talk about in 9.3 is that there's a second way of calculating chi-squared. So the way that we had calculated it before kind of built on prior knowledge of developing like a z-score, whereas this formula skips that. It's kind of a faster formula where it's just the sum of observed count minus expected count, quantity squared, divided by expected count. And so now we're going to use that idea in this section 9.4 of the worksheet, where we're looking at birthdays and whether or not they are equally distributed throughout the days of the week. So for question number one, that's of course kind of a review question, and you should be able to figure it out from the context of the first paragraph. For number two, what is the categorical variable of interest, and what are the possible categories? And so that's again built in that paragraph, and figuring out what are the categories is an important step of this project. So for number three, stating the null and alternative hypothesis, that will be very similar to the sort of hypothesis, null and alternative hypothesis from your reading. But instead of there being 6 categories, there should be 7, since there's 7 days of the week. Okay. For number 4, write down your own birthday and those of up to 9 of your family members or friends. And then number 5 is similar. Do an internet search for day of birth calculator, and then use that to calculate the day of the week for those birthdays. And you should have answered those in the survey question already. So for number 6, then combine your results with those for the rest of the class and enter those results in the table. So every time this class is taught, we'll have different data for this worksheet. And so for these videos, I'm going to show you data from when I taught the class this past fall. The fall of 2025 is when I'll show you the data for that. But your class's data will be different from this data that I'm going to show you. Okay, so for instance, the data that I have, if it works, well, it's strange, is this. There we go. Let's see if we can zoom in so you can see it better. And we can shorten that and shorten some of these. And then just shortening them, we can see that there's a total over there. Let's shorten that. Okay, that covers everything. All right, we can see everything there. So in the fall of 2025, when we combined all the people we knew of their birthdays, we had 19 born on a Sunday, 31 on a Monday, 20 on a Tuesday, 20 on a Wednesday, 18 on a Thursday, 25 on a Friday, 24 on a Saturday. So we had 157 birthdays total. Okay. So that would be, number 6, you'll have, for your class, your numbers will be different. Okay. Then, let's see. For number 7, if the null hypothesis is true and the birthdays are distributed equally over the 7 days in a week, then the expected count for each day will just be the total number of birthdays divided by 7. So you see here, this equation is the total number of birthdays divided by 7. And it's got the dollar sign, so I could drag it over and have them all be the same. So it's 22.43 all the way across. And then, so we, for your homework, for your data, you're going to fill that in there. is the validity condition of all observed counts, cell counts being at least 10 met? If not, what can you do so it is met? So in my case, with my data, it is met. And if it's not met, think about, go back to what the validity condition is from when we did 9.2, and think about this is only one condition, and so what would need to happen in order for it to be met. Okay, now we've got a little definition here of a goodness of fit test is used to compare observed counts for a categorical variable to hypothesized probabilities. This sort of thing is used often in polling when you know census data about the demographics of an area, and then you have a sample and you say, like, does my sample match the demographics? Did I get the same number of people of different ethnicities that I should get based on census data? And that tells you something about if your sampling methods are good or not. Okay, so number 8, comparing the observed and expected counts. Does it seem that the data gathered would be likely, assuming the birthdays are distributed equally? So this is this question is a conjecture question. So just answer it to the best of your common sense and your wisdom of the world, and it's not going to be graded too harshly because it's your conjecture. Okay, now for number 9, you will now conduct a simulation analysis using the mean absolute difference, MAD, type statistic to compare the observed and expected counts. To find the MAD statistic, we're going to do find the MAD statistic value for your data, complete the table. So do absolute value of observed minus expected. So that's what I did here. So I did it with the function ABS, which is absolute value, and then I did observed minus expected. Okay. Calculate the MAD statistic. All right, so my MAD statistic is this number then divided by 7. So the MAD statistic is obtained by finding the average of the absolute value of the differences in observed and expected counts. Calculate the MAD statistic. So then I take here, I do the average of all of those mean absolute values. Simulate. Now you could spin a spinner with 7 equal sections to find out what values in the MAD statistic could happen by chance alone, or you can use an applet. So if you don't have a spinner with 7 equal sections available and a ton of time on your hands, then let's go to the applet. So we'll go to the goodness of fit applet. So goodness of fit. And we'll clear the data. Enter 2 column names, e.g. category count, and then specify each category count, and then specify each day of the week. Okay. All right. So each day of the week followed by a space and the count from your sample. So day of week, and then day of week, and then count. And so then we have Monday. So then I'm going to move this over here. And we've got Monday is 19. Tuesday was 31. No, Monday. So Sunday. I'll fix that quick. Sunday was 19. Monday was 31. Tuesday was 20. Wednesday was 20. Thursday was 18. Friday was 25. Saturday was 24. use table. Okay, and then maybe I want to have shortened abbreviations so that it's easier to see them in the bar chart, for instance. So if I just do the first 3 letters, then I can distinguish them. So I'll try that. That looks way better. Okay, now doing that. Okay. So in the right panel, check the box, show sampling options. All right, set the number of samples to be 1, press sample, show sampling options. Okay, number of samples, 1 sample. So, what is the resulting most recent sample MAD? So, most recent sample MAD, no, a statistic is not max minus min, it's MAD. Okay, so most recent MAD for that data is 1.765. Now change the number of samples to be 999. And this will produce a simulated Snell distribution of 1,000 MAD samples. So the thing you should present for part C is that number that was right here earlier when you did just 1 sample. Okay, strength of evidence. Where does your observed MAD statistic lie in the simulated null distribution? So my MAD is 3.63. And so, which again shows right here as well. And so I'll do there, and then count. Now, why am I doing only greater than? Well, MADs can only be positive numbers because we're doing absolute value. There's no left side of the distribution. To be more extreme, when you're doing absolute value, is to only be more positive. Closer to 0 is less extreme. So, count samples and press count, and so then present that number. So I've got a p-value of 0.4210. Now, so let's see, there's a key idea there. Now, based on the p-value obtained in number 9, do you have strong evidence against the null hypothesis? How are you deciding? I do, in my case, with my data, I do not have strong evidence against the null hypothesis. And I'm deciding that because my sample is fairly plausible because the p-value is large. Okay, I'm going to stop recording and record the next video. I'm on the simulation goodness of fit using chi-squared next.